Battery recycling laboratories involve multi-layered risks, including energy storage hazards, chemical hazards, dust exposure, and waste management challenges. Therefore, it is not enough for a student or researcher to know only the procedure. They must also be able to correctly interpret labels, safety data sheets, waste classifications, and relevant legal requirements. In this presentation, we will focus particularly on EU Regulation 2023-1542, the GHS CLP system, and the practical use of SDSs. Regulatory literacy is a practical safety requirement in the laboratory. If a sample is not correctly identified as lithium-based, nickel-cadmium, or lead-acid, then storage, PPE, waste segregation, and emergency planning may all be incorrect. In battery recycling, a single material may present electrical, chemical, and environmental hazards at the same time. Therefore, regulatory knowledge is essential for correct risk control. Regulation, EU 2023-1542 is relevant not only for industrial recycling plants, but also for university laboratories. It provides a practical framework for the safe collection, segregation, storage, and handling of waste batteries. In this way, the regulation supports safety-oriented laboratory practice. Waste lithium-based batteries must not be considered safe simply because they appear discharged. Residual energy may remain, internal short circuits may develop, and mechanically damaged cells may heat up later. For this reason, storage is an active safety control, not just a logistical task. Students must understand that damaged, swollen, leaking, or uncertain condition lithium-based batteries require isolation, ventilation, signage, and traceability. The GHS and, in Europe, the CLP system were developed so that hazards can be read in the same language by everyone. Their most important contribution is that risk is interpreted not subjectively, but according to classification logic. In battery recycling, a student must be able to distinguish a corrosive leach solution, toxic metal-containing dust, or a flammable organic solvent. Pictograms are not decorative. They are the first gateway to control measures. The SDS is one of the most fundamental operational documents in laboratory safety. Students should use it not as a formality but as a decision support tool before starting work. For example, before working with a solution, it is not enough to know only its chemical formula. The SDS systematically provides what to do in case of eye exposure, which extinguishing media are appropriate in a fire, which glove type should be selected, and how the material should be stored. For this reason, the ability to read an SDS is a core learning outcome in undergraduate safety education. Hazard communication is not a passive reading exercise, it produces operational decisions. When you receive a sample, first you see the label, then you read the detailed risk information in the SDS, and then you use the relevant SOP to standardize the operation. If the operation is higher risk, the permit mechanism comes into play. In other words, in good laboratory practice, information becomes procedure, and procedure becomes safe behavior. If students understand this chain early, a significant proportion of experimental errors can be prevented before work even begins. In this first presentation, we saw that safety in battery recycling laboratories begins with regulatory literacy and hazard communication. When labels, SDSs, SOPs, records, and regulatory awareness come together, laboratory behavior becomes systematic. However, students must first gain this perspective. Safety begins not with equipment, but with correct identification.